Up next, we have an incredible project that we'll be presenting. We've got Arjun Bhuptani joining us from Connext. He's a co-founder, and he'll be speaking about Connext's instant cross-chain communication for Ethereum L2s. So this is a project we are really proud to be working with and are excited to hear more about what he has to say. So I've just added you to the stage, Arjun. Hey,
hello.
how's it going?
Hey, can you guys see me and hear me?
Perfectly.
Awesome. Yeah, thank you so much, Aiden.
Thank you. It's such a pleasure to have you here. I'm going to turn off my camera and mic, and please just take it away.
Okay, awesome. Let's see, I have some slides. Let me get them up and running. Okay. All right. I hope everybody can see this. I've given a talk before where I thought I was sharing slides the entire time, but I wasn't.
So good thing we're here to assist. Unfortunately, we cannot see the slides.
Okay.
What browser are you using?
I'm on Firefox. Maybe I should just share the window instead of the whole screen.
I'll let you know as soon as we see it.
Anything?
So nothing yet. I mean, one of the easy kind of solutions here is maybe using Chromium or something like that.
Let's see.
There have been issues with it.
Yeah, I can switch over to Chrome if that helps.
Yeah, no rush at all. Yeah, take your time. So yeah, just maybe I can talk about the rest of the schedule for today. After Arjun, we have James Prestwich joining us, who's a builder at Cello. And James will be talking about cross-chain communication. We then have Varul Kirpalani, who is a tech lead at Protocol Labs, who will be discussing TestGround, a platform for testing P2P and distributed systems at scale. After that, we have Rob Habermeyer, who is a co-founder of Polkadot and from Parity Technologies. After that, we have Jelena Durek speaking about the new world struggles to be born, coordinating in a time of crisis. And Jelena is an operations manager at Informal Systems. And ending the day off, we have ChainSafe's own Lorena Mance, legal counsel, and Cindy Chow, lead designer, talking about an overview on challenges regarding fraud in crypto/securities. So yeah, Arjun, great to have you back. Perfect. We got the screen and everything.
Awesome. Okay, cool.
So I'll get out of here. Let you get to it. See you soon.
Yeah, thanks a lot. Yeah, it turns out Firefox has some pretty intense screen sharing restrictions. Didn't realize that. Cool. Well, thank you for having me. I appreciate you guys having me here. I'm Arjun. I'm one of the founders of Connext. Today, I'm going to be talking about a new network that we've just put onto testnet called Vector. Vector enables instant cross-chain communication between Ethereum layer 2 chains and also different layer 1s. Basically, can serve anything that's Turing complete. So it's a pretty exciting development, especially as we get into this new phase of having many, many, many more chains. Let me see if I can full screen this. Might not be able to. Okay. Okay. Getting started. So I think the context for a lot of this is that no matter how things shake out, regardless of whether you're a proponent of like a rollup centric Ethereum future or ETH2 with a bunch of different shards, or like a plurality of chains where you have a bunch of different layer 1 ecosystems, or Polkadot or Cosmos. The bottom line is, I think one thing, what we're kind of starting to realize from a research perspective is that there's like physical limitations to having a single global consensus system that everybody runs their state on. And the only way to get out of this is to have a multi-chain world. And by that, I don't necessarily mean that there are a bunch of different chains with different validator sets, but at the very least, there are a bunch of different chain-like environments that have their own isolated state, that need to then communicate that state with each other. And this brings up this new core problem, which is how do you actually communicate state between different chains? How do you actually take value, liquidity that exists on a single chain and then move it to a different ecosystem? So in the Ethereum space, this is actually increasingly present as we move towards like a more layer 2 enabled paradigm. What happens if you have your balance in MetaMask on top of Arbitrum and you need to call the Uniswap contract running on top of Optimism? As a user, this is a pretty awful user experience, not only because you now need to understand the difference between Arbitrum and Optimism, which is something that pretty much no user ever wants to do, but also because for the Ethereum layer 2 specifically, there's also this additional headache of timeouts to get into and out of these systems. So getting out of Arbitrum, for instance, will take at least a few hours. Getting out of Optimism could take at least a few hours. I think in some cases it's actually up to a week. In ZK rollups tend to do a little bit better. But it's still nowhere near what you would want to see, which is like a single block, ideally, to get into and out of these systems, and then even ideally even lower to be able to communicate across them. So in the example that we mentioned above, if you want to get from your funds from Arbitrum to call a contract on Optimism, you need to exit Arbitrum, which can take like a few hours at least, if not up to a week. Then you need to subsequently pay money and take time to get into Optimism, rather than being able to go directly. Ideally, what we want here is actually just a shared routing layer that allows you to move value between these chains, right? We want a consistent standard that everybody enforces that says, okay, if I have value on so-and-so chain, I can get it to some other chain simply by promising it to somebody, and swapping for value on a second chain. This, as it turns out, is easier said than done. But we have the good thing is we can draw upon like existing networks like the internet itself to figure out how should this be built, how should this be structured. So now taking a little bit of a step back, this is kind of a little bit of a background of the problem statement and of the direction they're going and why this issue exists. So let's start now looking at Connect specifically. And also state channel networks more broadly, and then like Ethereum layer 2 chains as well as other chains. Now everybody, generally most people have a rough understanding of how like a blockchain works. Any chain is effectively a consensus system made up of a bunch of different validators. Those validators check to make sure that everyone that the state that's being put into a subsequent block is correct and is valid and isn't actually destroying anybody's value. And then everybody comes to consensus on this. Generally, Ethereum scalability solutions and most other scalability solutions out there have a similar pattern where they basically like scale up like horizontally. And there's the pattern here is very, very similar to like how you scale up servers in a server stack. You basically just add more servers, and you add like the ability to communicate between them. And that's kind of what like Ethereum scalability solutions do. It's like in many different ways, they allow you to create more chain environments where you have their own isolated consensus systems, and that can happen either via side chains, like things like XDAI, where you're basically just running an entirely separate chain with a separate validator set, or plasma chains like Matic, where you have a separate chain, separate validator set, but then there's basically an operator that is like held. Crypto-economically held liable for funds getting into and out of the plasma chain. Or you have things like rollups, which are a little bit more akin to like containerization / virtualization environments, where like you're not actually achieving consensus between like a bunch of different validators, but you're effectively emulating that consensus exists, and instead you're falling back to the validator set of Ethereum itself. And in all of these cases, like you can kind of see that it's really kind of, to the user, it looks like the same thing, right? It's basically Ethereum faster. And in all of these cases, the way that you're building these things is you're like either forking Geth or you're forking Ganache. So really, like from a user perspective, all of these things are kind of the same thing, right? Like it's a version of using Ethereum, but it's faster and cheaper. And the added headaches are basically like nuances around security that many users will not understand. It's really up to us to be the ones who kind of say, okay, well, this is secure, this isn't secure. Channels are a little bit different, and Connect specifically is a little bit different. unlike many of the projects in this space, Connext is not actually a chain. It's not a chain emulation environment. We don't run anything related to Geth or Ganache. We don't run anything related to Bitcoin, like the actual Bitcoin core stack. And that's a pretty big break from like what most of the projects in the space do, because in general, almost everything is like originally forked for Bitcoin. I think that's actually really important, because that's a part of why channels are so hard to build. That's a part of why like it's taken a long time for people to get to a position where like you have like fully working stateful state channels on Ethereum that work in a generalized way. But more importantly, it also helps explain why this type of technology is actually might be suited to solving this problem that other chains may not necessarily be able to do as easily. And that's the core reason for this, is that instead of being a chain, Connext is a peer-to-peer network that allows you to do point-to-point communication. Basically, it's a network of unbreakable commitments. I develop a relationship with another person. That relationship is a channel, a state channel. In that relationship, I have funds locked up, and I'm making, when I make state transitions in that relationship, what I'm basically doing is promising to that person, or committing to that person, that I'm going to pay them at some point in the future. And the great thing about these commitments, and this is kind of like the core property of why state channels are their own isolated, like trustless mechanism, is that those commitments are totally unbreakable, right? Like provided you make some assumptions about the chain, like the chain itself can't be censored and the chain is fault tolerant, et cetera, et cetera, et cetera. Provided you make some of those baseline assumptions about the chain, any commitment that you generate in a state channel will always be able to be resolved. And that's actually pretty powerful, because it's not just this relationship that you have with one other person, but you can link many of these relationships with each other. So for instance, here we have, from left to right, like Alice, Bob, Charlie, David. Alice and Bob can have a state channel between them, which is a bilateral relationship, and then Bob and Charlie can have a state channel between them, which is another bilateral relationship, and Charlie and David can have another state channel. And what's really interesting about this is that because you have the ability to do any arbitrary type of conditional transfer in each of these channels, you can actually make it so that Alice can transfer to Bob conditionally upon Bob transferring to Charlie, conditionally upon Charlie transferring to David. So you have this like you can have like hopped value transfer that goes over multiple different intermediaries. And this looks really, really similar to the internet, right? On the internet, you have a bunch of service providers that make up kind of like the backbone of the internet, and those are routers. Routers forward data packets, and when you are connecting to another person over the internet using TCP/IP, what you're actually doing is like you're connecting to some local router, which is connecting to another router, and so on and so forth. And you're basically pathfinding through this network to be able to get to your required destination. And what's interesting is that on the internet, you have these routers may be running on like totally heterogeneous networks. So you actually might be able, this is part of the reason why like you could do internet-based payments, and you have things like Twilio, which allow you to connect to phone networks, and like other kinds of different network ecosystems that are not actually the same, and they don't necessarily all need to be running TCP/IP. And instead you have this like broader network of things that just has this shared communication layer that allows you to interoperate between these different types of ecosystems. And the same kind of core principle exists within channels. You can run the same channels, the exact same system on any Turing complete chain. This is the exact same system that we're running today, and that's really, really powerful. So rather than just having this earlier system where we have just like Alice and Bob and Charlie and David all on Ethereum with each other, or on whatever, Polkadot, Solana, anything. Instead, you can actually have it so that Alice and Bob's relationship is on Ethereum, Bob and Charlie are on Matic, Charlie and David are on Scale. And from the perspective of the protocol itself, there's actually no difference at all. It's exactly the same thing. The protocol basically just says, okay, I have a connection to the chain. I'm going to try to make RPC calls at some point in the future. I'm going to make a commitment that can be called to this chain. But as long as you're generating commitments that can be resolved on the chain for any specific channel, it doesn't matter where those channels are. And you're able to transfer from Alice to David here in exactly the same way that you were able to transfer before, where everybody was on the same chain. And it's actually pretty interesting, because from the perspective of each different party within the chain, from the perspective of each channel, you literally cannot even tell that these transfers are going across chains in the first place. So we started exploring this concept a little while back. I don't know if everybody remembers, but there was Reddit did this like scalability challenge for the Ethereum space where they pitted all of the Ethereum layer 2s against each other. is a really, really interesting thing because there was a bunch of layer 2 systems and also the layer 1 chains that came out of the woodwork that nobody had really seen. The requirements that Reddit had posted were pretty intensive. And so like everyone had to kind of either build a custom system or show like the best of what they could do in order to be able to show that this was working. And there was a very, very high bar that was set as a result of like everybody doing this. I think so when we looked at that challenge, when we looked at the things that other projects were building, we kind of realized, okay, the Reddit's core requirements are associated with basically having a Turing complete chain-like environment, like running Ethereum but faster, right? They wanted to mint assets, transfer them, and then burn them. And that's like general, like you can do that within a channel, but like generally speaking, from Reddit's perspective, really what they wanted was everybody to be able to get access to points, see how many points another person has. Everyone comes to consensus on these assets that are minted, and then eventually comes to consensus on them when they're burned. So rather than building like our own custom system, we thought to ourselves, okay, well, maybe this is an opportunity to explore other use cases for channels, which actually fit into this layer 2 pattern more concretely, and also fit into like multiple chains, like a larger multi-chain ecosystem more concretely. So we built Spacefold. This is actually a GIF. I guess it didn't translate to PDF very well. I didn't think about that. But Spacefold was like a really, really simple UI that was built on top of our existing old Connect v2 code. We kind of hacked it together, and the idea was allow users to instantly transfer between Ethereum testnets and like 5 different testnets of different like upcoming Ethereum layer 2 solutions. So we supported XDAI, Matic. Actually, we supported the mainnet XDAI chain, Matic, Arbitrum, Optimism, and Scale. And then we had kind of done a little bit of a write-up about what it would take to support like Turing complete ZK rollups as well. The idea here was we wanted to explore how users interact with like being able to move funds across chains really quickly, and see if this was actually something that was even interesting in the first place. And under the hood, like the idea was it was very similar to what we were talking about earlier, where it's like you have 2 different channels, or maybe multiple different channels. There's an intermediary connects node that kind of like sits and provides liquidity on 2 different chains. And you have Alice basically deposit into a multisig, send an off-chain update to Bob, saying, hey, like I want to, in this case, Alice and Bob are the same person because you're just swapping with yourself. But send an off-chain update to yourself saying that, hey, I want to pay myself on another chain. And then the connects node would like provide liquidity on the second chain and exit. Fairly simple construction. Of course, because we were doing it with so many chains, there was actually like a lot more going on. We had a bunch of, basically we're spinning up like 6 channels. Actually, it was more. It was like 8 channels every single time you open the web page, which is not very efficient. And like I said, this was a very, very hacky demo. And the idea was just like allow users to move from Rinkeby to Scale or Matic or DexDai, whatever, instantaneously as part of this. When we put this out, to be honest, we didn't really know what we were expecting. We kind of just wanted to explore the use case and play around with it. We were more interested. We were actually like much more heavily focused on our other target market, which was like peer-to-peer micropayments. But this blew up. Like a lot of people, we kind of realized that this was actually a very, very big problem that a lot of people have been thinking about, but nobody really had been talking about yet, which is like, how do you actually adopt Ethereum layer 2 in the first place? How do you even adopt other chains in general, and move all of this? Like because I mean, most of the liquidity right now is on Ethereum. How do you actually build new ecosystems, new liquidity pools on other chains, unless you have an easy way to get into and out of those chains in the first place? This turned out to be like a huge and pressing problem for a lot of DeFi protocols who said, hey, like, we might be able to eventually transition to Optimism or Arbitrum or some other chain, but what does it look like for our users when we do that? How do we actually get them to get into this and out of this ecosystem? Because one of the biggest and most powerful things about crypto is that once you have this like steep onboarding curve where you need to like, for Ethereum at least, you need to and I recognize it's a very Ethereum-centric talk, but for Ethereum, at least you need to download MetaMask and like get onboarded with ETH and et cetera, et cetera, et cetera. And like, but once you do that, everything is actually pretty insanely seamless. So how do you take that user experience where like you just have a MetaMask account and you're just taking that everywhere with you and turn it into something that works when users are across multiple different chains as well? That was kind of what we learned as a result of Spacefold. And we started immediately thinking about, okay, how can we turn this into a full network? How can we actually solve this core problem for everybody as part using state channels as part of this broader proliferation of like like a multi-chain world, like regardless of, like layer 2 chains, shards, or anything like that. So we built Vector. Vector is a full cross-chain and layer 2 routing network. Basically, the idea is allowing users to route value between different layer 2 ecosystems, different layer 2 chains, and also other layer 1 chains, basically anything that's Turing complete. And the core ethos that went into this was that we wanted to understand, okay, in the same way that that TCP/IP is a shared communication layer that is used to connect heterogeneous networks and the internet, we can have Vector be this shared communication layer that connects different chains within this larger ecosystem. And there's something incredibly powerful here, because as a developer, and it's really the developers that benefit the most from this kind of technology. As a developer, though of course this bubbles up to like in user experience to the end user as well. But as a developer, the process of needing to like get different assets and figure out how you actually interact with different chains when you're trying to build an application that runs on like leverages both Filecoin and IPFS and Ethereum and like the Graph and Matic and a bunch of other things actually explodes in complexity. And this is something that like we've seen both ourselves as a result of like working with projects that are doing that, and also have kind of seen from the ecosystem. The core idea behind Vector is very, very similar to the internet itself. We have a network of routers. Those routers provide liquidity and forward data between chains. Routers are effectively like service providers, very, very similar to routers on the internet. They have some limited context into what they're actually forwarding, but it's actually not very much there. For the most part, they're like blindly forwarding data. And the ideal case is that eventually they know very little about what they're doing beyond just a basic check to see if they have the liquidity to forward transfers in the first place. And what's even more powerful about this is that rather than just using something like a POS bridge or something like an on-chain atomic swap, routers aggregate liquidity and network effects from the rest of the ecosystem as well. So like if I'm running a router that supports Ethereum and Matic, and then Bob comes online and runs a router that is supporting Ethereum and XDAI, that means now the entire network supports Matic, Ethereum, and XDAI. So a user coming into this network now has access to all three of those chains. So this aggregates liquidity and network effects really, really quickly. It's extremely powerful because you do like one single integration, and now every single person in the network now supports that chain. The overall vision that's been kind of driving this has been, we don't want users to ever know that they're interacting with multiple chains, because the bottom line is users just don't care, right? Like high fidelity users in the ecosystem right now might say, okay, well, I want to check out ZK Sync, or I want to check out Loopring, or I want to check out, like Polkadot, or I want to check out so-and-so. But the reality is that even those high fidelity users in most cases don't really understand the underlying technology. And even if they do, like, they're really just picking one over the other because of like some slick branding or marketing effort. And more importantly, I think in the long term, as we scale out to like the larger early majority user base, it's not really going to make sense to any new user who is joining the ecosystem that they have funds that are sitting on Near, for instance, and so they have funds on Near and Solana, and they want to interact with a contract that's running on Arbitrum or Optimism, and like the concept of needing to move funds, to bridge funds from Near to Ethereum and then from Ethereum to Optimism is just absurd to them, right? It's never going to make sense. Ideally, what we want is this situation where you have the exact same user flow that you have currently. You have funds in a wallet. The user just sees an aggregated balance. They don't really need to know that these assets may or may not even be on the same chain as each other. And then they're able to call contracts or interact with technology running on different chains, applications running on different chains, without where like all of the swapping and all of the routing to go to a different chain happens in the background. And this is something that we're working on actively with wallet providers right now to come up with a good user experience where ideally what it looks like is basically the exact same as what you're doing today, where you just sign a MetaMask transaction, and instead of just saying the contract address that that transaction is going to, it also gives you a chain ID. That's it. That's the difference. What's next? So I actually didn't have time to put together more slides for this, so I'm just going to talk through it, and then also happy to jump into more questions about it afterwards as well. I think we just went live on testnet with Vector a couple of weeks ago. I think we're now we've already started the process of integrating with a couple of chains. There's two chains or a bunch of chains. There's two layer 2 ecosystems that are fully onboarded, and we'll be announcing them soon. And then there's more coming kind of in the pipeline as more testnets start coming up. We have started an audit already, courtesy of ChainSafe, actually. We expect that to be done, and expect like most of like the audit work to be completed before the end of the year. And the target is to kind of hit the ground running with this, with a couple of live applications in January. From there, a big part of what we want to do initially is just bootstrap the network and get some of this, like the early network effects, and also get this up and running, because we recognize that this is an extremely pressing problem for anybody that's using Ethereum layer 2 right now. We've kind of elected to basically have like a minimum viable network where we run with like 5 hard-coded routers first, and we're still looking for folks to do this. Basically, these routers would be like slightly larger liquidity providers that are institutional, have like a little bit more experience keeping nodes online, and initially these will be like hard-coded. So we'll actually have like their addresses, their routing information, what chains they support, how much liquidity they have, et cetera, like uptime, things like that, listed in our documentation until we get the network going. So that's the initial stage, is this like small five node network, which tries to serve as many chains as possible, and then from there, get this initial adoption, prove out the use case with dApps, show what the user flow actually looks like, and kind of solidify that with the help of like dApps and wallets, and then scale up the number of routers. We have some good ideas on how to do this. If anybody is interested, like there's some really interesting stuff that's come out of Lightning lately, called Lightning Pool. Basically, the idea is, rather than having right now you have like routers manually open channels to users and provide liquidity to them. In Lightning Pool, you actually have a market-based mechanism where like users just put up asks for channels, and then routers bid on them. And because of that, now you have this like more decentralized ecosystem where routers don't need to develop expertise or like one-to-one relationships with users. They can actually just like blindly turn this thing on, put some liquidity in it, and it'll just work as long as it's connected to the market. And then secondly, you have a little bit more predictability for the routers, because as a router, one of the hardest things to understand is like, okay, I'm gonna lock up my liquidity here. Is it actually going to be routed over? And in this case, you're kind of guaranteed that it is, which is pretty nice. So that's the direction that we're headed. And as soon as we've implemented our own version of the same kind of concept, we expect to scale up the number of routers really massively, because at that point, running a router is pretty much just running an Avado node or whatever, just throwing it up on an AWS server or anything like that. Really, you could run it on like a Raspberry Pi if you wanted to, and then just plugging in some liquidity. Yeah, so that's kind of our roadmap from here on out. Is we going live in January. We'll have material use cases live with some like DeFi projects where you'll be able to see this working on different chains, and we're really excited to see the kind of feedback that people have as a result of this. If you want to try it out yourself, setting up a test router is pretty easy. It's literally 3 lines of code. You just clone the repo, and then make start, and that should set up like a local ecosystem where you can test test like your hardware requirements, and then 2, also do test transfers between 2 local Ganache chains. And then we can also help you work through setting things up like more in more of a prod context if you reach out directly, and we have some docs available. This documentation link is actually out of date. We have new docs that will be moved here soon. But for now, I would say just join our Discord, and then like we can help you out if that's something that you want to get going with. Cool. I don't know how I'm doing on time, but I tried to leave some time at the end for questions as well, which seems like we're doing.
Yeah, well, thank you so much for that talk, Arjun. That was really amazing, and I'm just so excited to see what comes from all of this technology. We're just so proud to be working towards this vision and really realizing, as you said, a lot of these conversations that you've been having, that people are really just coming to the realization of how important they are to maintain composability across so many of these new upcoming protocols. So beyond all of these exciting projects, to have that glued together is vitally important. So we do have a bunch of questions for you in the Q&A section. So let's start with the first. Aren't capital requirements for this extremely high, as routers must maintain liquidity pools on each chain?
The capital requirements are the exact same as if you did like on-chain atomic swaps, or if you were running like a custodial exchange, or if you were running basically like any sort of system where you're providing liquidity. So it's not too bad. And like the capital requirements for channels typically are high, and we consider them high because there's actually like a broader thought process here, which is like channels in the past were generally thought of as like a solution to payments specifically, and like micropayments more generally, just because like the capital requirements. And like in general, the trade, like what you're trying to do there is compete with like on-chain gas costs, right? So you're basically saying, I'm going to lock up so and so amount of liquidity, and like I'm going to try to route as many transfers as I can using that liquidity, ideally billions, because then that way you don't have to like incur on-chain gas costs, which actually drive most of the cost basis for a system like this. However, in this case, you're not actually competing with on-chain gas costs. You're competing with like the possibility of being able to move value between chains in the first place, and that's actually something that's like much more valuable intrinsically. So you can charge a much higher spread on it, and also like people are generally more willing to provide liquidity for something like that than for just a simple transfer in the first place. In general, I mean, I think basically the options are like if you do this, you get instant exits from these systems, and that instant exit from the system will always be cheaper than trying to borrow liquidity against like a 30-day exit or like a 1-week exit, because the instant exit doesn't like the capital lockup of the instant exit is much lower than the 1-week lockup that you would incur from like trying to exit optimism.
Awesome. Yeah, I mean, also what you've described with the pools, for those who aren't familiar, also kind of help with this problem as well, by providing more access to what is that liquidity as well. So the next question we got for you is, what disadvantages or trade-offs are present in a P2P chain / P2P relationships in comparison to a normal chain ecosystem?
Yeah. So I don't know if it's so much about advantages and trade-offs as it is about just like a completely different style of thinking. It's a completely different style of ecosystem in the first place. So like for instance, right, there's like a lot of things that like this is a way that you can think about the trade-off space for like layer 2 scalability in general, right? This is a big part of the reason why like when you think of layer 2 scalability for Ethereum, and like most people when they think of that think of like, okay, let me do Ethereum but just faster. And channels doesn't really fit into that. And the reason for that is that like, because it's not a consensus system, you don't have this ecosystem where everybody has access to the same shared global state. You can't run something like Uniswap on that, because in Uniswap, like it's a peer-to-contract system. You have this on-chain shared global contract state that everybody is interacting with and everybody needs to know about. You can't ever do that in a channel, because in a channel, the state is shared only with your direct peer. Now, that's one of the reasons why it's actually much more effective for something like this than for trying to do just abstract scalability of Ethereum itself, is that like in this case, we're only specifically talking about transfers of value or contract calls across chains in the first place. And in that limited use case, you don't necessarily need everybody to have access to your state data. I think I would say like the biggest trade-off is like figuring out how. So one thing that we're actively in the process of trying to figure out how to do is how to outsource liquidity for routers. So like right now, there's a tight coupling between like liquidity providers and router operators. You have to do both at the same time, because a router is effectively like is effectively a peer within the network, right? So they need to be like, in order to be able to be sure that their own liquidity is secure, they need to be like self-incentivized. They need to be signing for themselves to be able to ensure that transfers are propagated across the network properly. Ideally, what you want is to decouple these things, because the overlap of people that are capable of running nodes and the overlap of people that have a lot of money is actually surprisingly low. Like, unfortunately, there aren't a lot of like really like, there are more now than there were before, but unfortunately there aren't a lot of extremely rich people that are just like running nodes at home all the time. So because of that, like, ideally we want to allow for some sort of, basically very similar to like existing staking network, some sort of delegated staking mechanism where users can stake 2 routers and then earn a portion of the fees that the routers collect. That's something that we're working on. It's still like an area of very active research and hasn't quite been figured out yet.
Awesome. Well, thank you so much. And yeah, really excited to follow up. For anyone who does kind of want to see more about it, all of the Connect information is just down here on the bottom screen. I'm sure they're always looking for people to kind of talk to on their Discord as well. So thank you again, Arjun. And again, I just want to say how excited we are to be, a part of this journey, even if it is in a minor way. And we're just really excited to see how it all develops and where we go from here. So thank you so much for stopping by today. And I'm excited to have you here hopefully next year at CSCON 1 and to see how that year has affected Vector. So yeah, looking forward to talking soon.
Yeah, cool. Thank you so much, Aiden. Thanks for having me.
Of course, it's our pleasure. Talk soon. Bye-bye. Cool, so that was an awesome talk. Next up, we've got a man who was voted the best hair in Ethereum, a self-professed curry enthusiast. I'm trying to find you here in the chat, and a builder at Cello. Sorry, I'm having trouble finding. Oh, okay. No, I'm in the wrong tab. Oopsies. We've got the one and only James Prestwich joining us today. Where are you? There you are. Cool. Cool. So James, you should be able to share everything. So you're just muted still?
There we go.
Awesome. Well, thanks for joining us today, James. Really excited to hear your talk. Whoa, we've got some animations and everything.
I joined Cello and they gave me this whole brand package with animated GIFs and icons and, the whole 9 yards. So it's not so bad.
We'll take it away and we'll talk to you in a little bit. Thanks, James.
Perfect. Thanks, Aiden. Hey, my name is James Prestwich. I work on protocol at Cello, and a lot of what I do is bike shedding consensus systems. So I've implemented Bitcoin transactions in 6 different languages and a bunch of Ethereum library stuff. Mostly what I work on is cross-chain communication, and that requires a very deep technical understanding of both chains that you're working on. In my spare time, I got a degree in Japanese literature and have never given that up, even though it's not a huge part of my day-to-day work experience right now. Maybe I'll get back to that pretty soon. The goals for this talk is to give an intuitive understanding of these technical systems we call bridges, what they do, what they're for, and then segue into my favorite topic, which is the communication methods that underlie them. And to give a brief overview of how those work, and then go on to categorize existing work in this framework. So the idea here isn't to tell you about a product or pitch you on something. We're just going to try to do some first principles about bridges and cross-chain communication. So this is kind of the idea behind a bridge, right? Is we have some Bitcoin, we lock it up, something happens that causes tokens to be minted, and then you go use them in your dApps. And when you want your Bitcoin back, you just do it all in reverse. So I just mirrored the graph from the last slide and used it again. It's a cheap way to just get more slides into the presentation, take up a little bit of time. Okay, so what makes it a bridge? Like from these two graphs, what makes the bridge? It's this part, right? It's the minting and the burning. You have this supply consistency of WBTC that should be backed by locked Bitcoin, and TBTC works the same way. But what is actually the hard part is like this bit, the magic that happens behind the scenes that the user is never really aware of. And so if we want to like unpack that a little bit, what you actually have in there is two one-way communication channels. You have a message system that goes from Bitcoin to Ethereum, and one that goes from Ethereum back to Bitcoin. And all of the complexity of the bridge application is in establishing these dual simplex channels. Dual simplex is a complicated way of saying that these are two independent, so they're dual, and they're simplex, they're one-way communication. We use these dual simplex communication channels to make what we call full duplex, where you can send messages back and forth. This is all like trying to make an analogy to traditional telecoms. So we're using these two channels to establish the application, the bridge, what we actually want, minting and burning these Bitcoin tokens. But the bridge is a relatively small piece of the complexity. So I want to dig a little deeper into how communication works. More brand assets. We get this fancy confetti slide. We are sending messages from one chain to another. There's no way to know if the response is received. You're not going to get a message back on the same channel. So how do we actually send those with confidence that they're going to get there? What we would like to do, what we wish would happen, is that the Bitcoin and the Ethereum chains just talk to each other and nothing happens and it just works, right? Unfortunately, in reality, things are a bit more complicated. We have these trust boundaries. Bitcoin can't know what's going on off-chain. Ethereum can't know what's going on off-chain. Ethereum doesn't know about Bitcoin. Bitcoin doesn't know about Ethereum. We have to figure out some way to get the message across these boundaries. And we have to, because this is a trust boundary between the outside world and Ethereum, Ethereum can't validate incoming messages. It can't establish the truth of those without some very specific logic. So you can't just have the message go straight to the DApp, right? We have to insert some amount of processing into this to make it work. The DApp needs to know that the message is good. So now, we've gone from just a message sent from Bitcoin to Ethereum. We've introduced new steps. We have to dispatch it on the Bitcoin side, and then we have to process it on the Ethereum side. And we have to determine if that message is any good. If you're familiar with flowcharts, you're going to know that these parallelograms are input-output from a process, and the diamond is a decision point. Normally, a diamond would have two whiskers coming out from it, but for convenience and because I'm really lazy, anytime you see a diamond with only one whisker, just assume that the other path is the message is discarded and you do not communicate between chains today. So if you get a bad message, we're just going to throw it away. All right, so we want the Bitcoin chain to dispatch this Ethereum transaction, right? But it can't actually do that. Bitcoin doesn't have SecP keys. It doesn't know what an Ethereum transaction is, and it can't sign things or use smart contracts in any way, really. So we have to come up with some other system that's going to dispatch that transaction for us. And so we insert these new off-chain actors. Bitcoin is going to commit to some message that needs to be sent. It may not know where that message is going. It just knows that it has produced a message and committed it to the chain. Some off-chain actor is going to see that, decide whether or not they want to forward it, and if they do, dispatch an Ethereum transaction. And then on the Ethereum chain, we get that transaction, we start processing it, we see if the message is any good according to some definition of good. And if it is, we send it on to the dApp. If the off-chain actor doesn't see the message, chooses not to forward it, or if the message is no good, your message gets discarded and there is no communication between chains today, and you do not get a bridge today. Right. So the core problem here is that chains are passive, right? They only respond to things that are coming in. You send a transaction, it triggers some series of on-chain events, and the chain updates its state. The only outcome of a transaction in a blockchain is updating the chain state. It can never autonomously trigger other actions, which is what we want it to do. Communications have to be active, right? You have to send the message, you have to know that it gets there, and you have to have some sort of like expected response to it coming back through another channel. So in order to like make the communication system active, we need these off-chain actors that are observing chain state and forwarding messages to the other chain. And they must be spending Ether on TX fees to do this. So we've talked a bit about, like what is good. The Ethereum chain has to know this incoming message is good if it wants to act on it, right? So let's like zoom in here on the destination chain. And we rotate it sideways so I can make this bigger and see it in one slide. And the majority of the communication channel design, the majority of the bridge effort and complexity is in what makes a message good. When Ethereum sees this message that is ostensibly from the other chain that's been forwarded by an unknown off-chain actor for unknown purposes, how does Ethereum check that that message is trustworthy? Or in more concrete terms, how does it check that the message is actionable? At some point, the destination chain receiving the message has to commit. It has to say, yes, this is valid, and I will update my state as a result of this message being processed. We need to set, concrete, deterministic criteria, usually in Solidity, for how you do this. Okay, so we have a few different trust models for this. The simplest one is proof of authority. So in this example, I will sign every message Bitcoin sends, and I promise that I will do it correctly. And Ethereum can just check that these messages are signed by my keys. I think this is a great system. It's perfectly trustworthy because I trust myself perfectly. And so this is supposed to say James instead of relay. We'll just pretend it says James there. So in a proof of authority setting, messages are small and can be arbitrary. I can sign anything. I'm me. I decide what I can sign. And I can update that at any time. And they're fast and cheap to validate. The downsides are that there's a single point of failure. If I get hit by a car tomorrow, then James BTC is not going to be worth very much. Centralized points of failure are very censorship prone. And if, like I decide to run off with all the Bitcoin, there's nothing you can really do about it. So the failure mode is terrible. These are easy to extend into a federation where it's like six different people or 7 signers, in charge of these things. You have the Liquid Federation and the XDAI Federation and all these other kind of federated systems. But they're still trusted, they're still censorship prone, and there's still no recourse if the Federation decides to steal your money. So we'd like to do better than that. And so one of the intermediate solutions that's pretty good we came up with is stateless SPV. And what we're looking for here is not did James sign this message, it's someone is sending me a message. How much money did they spend to produce it? How costly is that message? I know, as a verifier, as the Ethereum blockchain, that if somebody spent $2 million creating a message, it must be pretty important to them. And I can probably trust it up to $1 million or so. The nice thing here is that Bitcoin and other chains with proof of work are creating that costliness for you all the time. And so the verification for this is very simple. You check that the message is syntactically correct, and then you check that there's a lot of proof of work on top of it. How much proof of work there is a security parameter that's adjustable. Essentially, all you're doing here is checking that somebody spent millions of dollars of electricity to produce this message. And if they did, it's good. And we can validate that message and forward it onto the dApp. We can decide to commit it to the chain state and the destination chain. So stateless SPV is really nice in some ways. It's small. It's no ongoing process. That's why we call it stateless, is it needs no outside information. And anyone can participate. Unlike proof of authority or federations, anyone can construct this SPV proof from Bitcoin, can go get those Bitcoin headers with the transaction in it. The cons is that it's proof of work only. It relies on this unforgeable costliness, the objective costliness that proof of work has and proof of stake doesn't. And in practice, because people have selected these really, really terrible proof of work algorithms like ETH-hash, it only works for Bitcoin, which has a reasonable, commonly used hash function for proof of work. So stateless SPV has this extremely narrow scope. It can only do one-way communication from Bitcoin to some other chain. And that makes it not very useful for the vast majority of bridges. And stateless SPV does permit forgery by wealthy adversaries. So you have to carefully parameterize your costliness requirement to ensure that it's high enough that it can't be forged, but low enough that it's cheap to verify. And that's a very delicate balancing act. And so the last method, model of communication that we're going to talk about is relayed SPV. So this is essentially the destination chain is implementing the sending chain's consensus process. You may have noticed that I talked a lot about proof of work in stateless SPV. It's because proof of work is Bitcoin's consensus process. It's how you decide what is true in Bitcoin. Relayed SPV is not just we're going to check for costliness through proof of work, it's that we are going to maintain actively in the Ethereum chain state, in the destination chain state, a model of the remote consensus process on an ongoing basis. So we actually have to bifurcate our processing here a bit, because we need this local view of the remote chain, and we need to update it and keep it up to date. For proof of work, this means tracking the latest block header. We get a new message. If it's a header, we're going to try to add it to our local view of the Bitcoin chain. If it extends a known header, if it is extending our local view, we're going to check the proof of work, and then we're going to update that local view. So that way, you have the Ethereum chain running a Bitcoin-like client actively. It's following along the chain tip, it's processing new headers, it's checking proof of work, whole 9 yards. And for regular messages, you're going to check if they're in the local view of the remote consensus. So you keep your local model of Bitcoin and you check if a specific transaction is confirmed in that local model. Then you can check if it contains a message and dispatch that message to the dApp. The validity here is coming from the actual consensus process of the remote chain. And this works for Bitcoin, for proof of stake systems, but not for non-Bitcoin proof of work systems for the same reason stateless SPV doesn't, because they've all chosen very bad proof of work algorithms. Okay, so we're going to maintain this relay where all the headers from the remote chain are getting relayed over to the destination. And we're going to keep a local model of the sending chain state where we can validate that messages were in fact sent. And we do that by running a light client that anybody can update. All right, so the pros here are, it's as good as the remote consensus is. If the remote miners or the remote validators, stakers, are honest, this relay will always produce correct results. If they're dishonest, it can produce incorrect results. And anyone can participate because the remote chain and its consensus are public information. And we get this really nifty thing for modern proof of stake systems where you get logarithmic complexity. I only need to process like this one header out of every 100 or a logarithmic number of headers for modern proof of stake systems. And there are very complex reasons for why that is, but it makes it extremely cheap to process. The downside, though, is we have all of this overhead, right? We're sending messages for some number of block headers. Those messages are expensive to process because you have to do a bunch of signatures for proof of stake, or you have to do a bunch of work for proof of work. And it relies on a trusted setup. So you have to kind of insert known good state, like a genesis block for the relay. And while you're maintaining it, if you fall behind, you'll need to redo that trusted setup for any proof of stake chain. This is a consequence of the kind of subjective epoch-based proof of stake consensus. But essentially, anytime you go over a certain number of blocks without processing a new message, you lose your trust in the remote consensus process. You need to update your relay. For Celo, it's once a day. For ETH2, it'll be every epoch, which is 12 minutes, I think. So you need to keep your relay up to date extremely often, or you lose the ability to validate messages correctly. All right. So while we're on the subject, what's sharding? We're expecting ETH2 to launch with shards. Those shards eventually will be able to communicate between each other. If we've established that there are 3 ways to communicate between chains, how does sharding work? Sharding is kind of what we call mandatory relayed SPV. So when you put this relay tracking the remote chain state into the consensus process instead of into the state. So if part of Ethereum's block header validation was that it had valid Bitcoin headers in it, that would be sharding rather than a relay. Typically in a sharded system, you get recovery from failures. So if we commit some invalid Bitcoin message, we would roll back to take that message out of the destination chain. And in ETH2, if an invalid transaction is committed in one of the shards, the beacon chain and the other shards will roll back to fix that and omit it from the history. So sharding is a kind of relayed SPV with failure detection and recovery. All right, and while we're talking about communication models, what about atomic swaps? To which I answer, what about them? Nobody likes them. Please stop asking. Okay, so we've got through the models section of the talk. I'm going to review the Q&A real quick before going into the last slide that I have. So let's see. Are any of these applicable and would clarify things right now? What improvements would I like to see in these networks to get to the ideal situation where communication is almost native? Sorry, Aiden, I'm trying to clear up any outstanding questions about models, and then I go into the last 5 minutes.
Okay, understood. Yeah, cool. Sounds good.
Cool. Yeah. So as far as improvements go, I've insulted people's proof of work choices a few times throughout the talk for very good reason. All of the proof of work chains with memory hard algorithms essentially cannot ever participate in these cross-chain systems, in relays, bridges, any sort of cross-chain application except via atomic swaps. So just right off the bat, I would get rid of all of those. And then for proof of stake systems, I think the key thing is that you need to be able to check the hash and signature algorithm of the remote chain. And everybody is using a bunch of different signature algorithms right now. BLS 12381, 12377, ED DSA, and a bunch of kind of unrelated things. So it would be nice if there were a standard that everybody followed there. Anyway, so getting out of models, I want to briefly touch on classification of existing systems. I just put together a little chart with most of the major ones that are out there in the wild right now. Running down the list, you have WBTC and RenBTC, where things are held in multisig by the company that runs it. So you get this kind of trusted federation with a small number of signers. For TBTC, we have stateless SPV, and it allows us to do a bonded federation on the round trip, the way back. Essentially, we're cheating by using the same one-way communication channel twice by verifying that the return trip completed successfully and penalizing people if it didn't. So rather than sending a message and then sending one back, TBTC sends two one-way messages. First is setup, and the other is did teardown work. If teardown didn't work, the signers get penalized. Cosmos IBC is going to be the first fully relayed SPV bridge between proof-of-stake blockchains. They've been working on this for at least 3 years now, and it's finally going to be included in the hub chain. Rainbow Bridge is Near's recent entry into this. It relays Ethereum onto, I have an error here. It should be relayed on both sides there. Rainbow Bridge relays Ethereum into Near and Near into Ethereum using optimistic fraud proofs. So the Near relay is somewhere between a bonded federation and a full relayed SPV. It has signers that are expected to do the work, but the signers are penalized by fraud proof if anything goes wrong. Solana's wormhole is currently in fully trusted, but will eventually move to the same model as Rainbow Bridge, if you believe their plans for it. XDAI, the POA network, is fully trusted federation. They're looking to move towards an open federation. And lastly, we have ETH2 deposit contract, which is just a trusted federation right now. There's no actual consensus level communication happening between ETH1 and ETH2. You have the open dynamic federation of ETH2 validators who are trusted to issue new deposits when ETH1 is moved. And you may notice I'm speaking at CSCON, but I haven't brought up Chainbridge in this classification. I have always seen Chainbridge as more of a scaffold and framework for building these things. It can be extended to work with any of these communication models. The goal of Chainbridge, in my view, is to provide a shared common foundation for the off-chain actions that communicate between chains. And I think that's really cool and useful. Anyway, that's the end of my slides. I'm going to leave up the classification slide, which I have unhelpfully titled terminology.
Well, thank you so much for that, James. As always, incredibly informative, and I really appreciate the way you've classified Chainbridge because I don't think people necessarily understand that. So I just really appreciate how you've approached this, and also just the educational aspect of all of this because, yeah, most people really don't, and probably still, unfortunately, will not understand a lot here, but at least know where to go to start to understand these things. So I really appreciate you taking the time to really cover all of this because it's incredibly important, especially as we're moving towards a world that will need all of these different tools. So thank you so much for this talk. And you've gotten a good hang of the Q&A section. So we got one more question for you, I'm sure you've seen, which is what are the challenges of creating a test suite for covering all the edge cases for determining if a message is good?
Yeah, this is a very good question, especially when it comes to Bitcoin, where most of my work has been. Bitcoin does not have a specification Instead, it has a C++ client that you have to go and read and or run to see what happens. So there's a huge number of challenges because we had to essentially develop from scratch a large corpus of test cases to check that our implementations conform to Bitcoin behavior. And it was really painful and unpleasant. This gets much easier in Ethereum and ETH2, where specifications are more common and more in-depth. It is much easier to implement an ETH2 Lite client than a Bitcoin Lite client because everything you need is right there in one document. Of course, it's also easier because ETH2 doesn't do anything right now, but that's a conversation for another day.
Well, that is quite the hot take to leave us on. I know many disagree with that statement, and maybe a few will agree. So we're going to maybe keep it at that, and maybe we'll slot you in for 2 talks next year, one on bridging and then one on Ethereum hot takes, where we just scroll through your Twitter.
Oh, actually, that sounds like a really good session.
So James, I just want to say thank you so much for joining us. Congratulations on the new work that you're doing and everything that you've been doing. And we're really excited to see how our work together can continue to evolve as we're bridging Celo to Celo in what is, I think, a really incredibly exciting way. So hopefully more can come out to the community soon about that.
Yeah, I definitely agree. Thanks so much, Aiden.
Thank you, James. And so for everyone joining us here and on YouTube, we're going to be taking probably around a 5-minute break. And next up, we have Rahul Kripalani, who is a tech lead at Protocol Labs and really just an all-around incredible person who will be talking about TestGround, a platform for testing P2P and distributed systems at scale. So we'll be coming back in about 5 minutes and starting out on that incredible talk. Thank you all for joining so far, and see you